Okay, so we've managed to characterize our symmetry transformation by saying what it does to the equations of motion. But this is not the most useful description we could have. You see, in quantum field theory, you'll be used to this by now. We don't usually refer to solutions to the equations of motion. We're usually doing some sort of a path integral, and it's the action that appears. So what we'd like to do now is we would like to actually start making statements about the action. Now, what is the relation between a solution to the equations of motion and the action? Well, if you remember the the Euler-Lagrange equations, so let me just write EL equations, and remember the Euler-Lagrange equations are our equations of motion. They are obtained by requiring under any first order transformation. So we shift phi into phi plus delta phi. That's a variation of the phi. And by first order, we're only going to keep delta phi, so we're going to drop delta phi squared. So the Euler-Lagrange equations of motion are obtained by requiring that under any first order transformation, we have the change in the action is equal to zero. So, solutions to the equations of motion minimize the action S. So now we've got a statement in terms of the action S. Equations of motion minimize the action S. So now let's turn this into a statement about symmetries. We can say symmetries take you from a minimum of the action into a minimum of the action. Okay? And now we've got a statement about symmetries in terms of the action. Now let's see what that would mean for the value of the action. Well, there's certainly some transformations that we can consider. Let's imagine, I'm going to imagine that I've got some action, S of phi, okay? I'm going to plot it here. So there we go. Maybe it goes like this. This is phi. And then imagine that I do a symmetry transformation. And that symmetry transformation takes phi into phi primed. So I take my field phi, I perform a symmetry transformation, and I get the new field phi prime. Phi need not satisfy the equations of motion. I've just picked up an arbitrary field and I performed the symmetry transformation. Under the symmetry transformation, S of phi would go into, so now it would be S evaluated at phi primed. And if we have the following, if this is S of phi plus a constant, then what would we have? Well, maybe this curve shifts up by a constant. So something like that. But the point is, okay, my drawing is not great. The point is, if it shifts up by a constant, then you can see the minima for the blue curve and the black curve lie at exactly the same point because they're just a translation in the vertical direction with respect to each other. So you don't change the horizontal location of where you get a minimum for the action. Okay, so this S of phi is that blue curve over there, and S of phi is that black curve over there. So if the symmetry just shifts this curve by a little bit, we're absolutely in business. We'll be mapping minima of the action into minima of the action. Now, when we say here constant, we mean constant with respect to what? Well, we mean constant with respect to phi. So let's just talk about this horizontal axis phi. What is that? So when we write phi here, we're actually mapping out different fields phi. So each point here is a function. It assigns a value to every single event in space-time. So it's the full function. So this would be a massive space, the space of all possible functions in our space-time. So we're just drawing a cartoon here by indicating phi with a single axis. And what we're saying is, under the action of the symmetry, the action shifts into a new action plus a constant. And when we say a constant, what we mean is, we mean independent of phi. Now, let's talk about precisely what that means. Well, imagine we were studying, I don't know, for definiteness, let's just say we're studying a scalar field in 4 dimensions, let's say of mass m. So this is d mu phi, minus 1/2 m squared, phi squared. I don't know, maybe there's some potential, totally up to you, that's perfectly fine. So this is the kind of an action that we are studying. How can we find a transformation which just shifts S by a constant? Well, imagine that under the symmetry, we find that this becomes S plus delta S. Let me not say equal. So under the symmetry, what does that mean? That means we shift phi into phi prime. Okay, that's the action of the symmetry. Then we evaluate the action on phi prime. And what we find is, let's just write this out a bit more carefully. S is equal to S of phi plus there's some change in the action as a function of phi. If that change in the action takes this form, if this changed action term takes the form delta S of phi is maybe equal to an integral d4x of the divergence of something, then you know that you can integrate this and you'll end up getting a surface term. So the entire contribution to this integral comes either from spatial infinity or the initial time or final time surfaces, but it's all just a surface term. Now, whenever we do our path integral, we imagine that the field is fixed on the surfaces at spatial infinity and at the initial and final times, so that the value of phi is fixed there, and this would count as something that is fixed, that doesn't depend on the value of phi. So if we're just getting a surface term, this would be a situation where S shifts by a constant. So what we know is we can now put down our most precise definition, and this is what we're going to use to actually develop Newton's theorem. We're going to say under a symmetry, the action changes by a surface term. Okay, and this is really all that we need to require if we're saying that symmetries map solutions to the equations of motion into solutions to the equations of motion. And it's because on the surface of the space-time, this is where the field is fixed. So, that would be fixed. So let me say it another way. All fields phi that you have on this axis here, when we plotted the action, all of those fields have the same value at spatial infinity and at the initial and final times. Good. Okay, one last comment. This is in fact not good enough to say that you have a symmetry in the quantum theory. You see, in the quantum theory, what would you typically be doing? Well, you're not interested. So classically, you would have a solution to the equations of motion, and you could evaluate any quantity of interest by evaluating the observable on that solution. In the quantum theory, you'd be calculating some correlation function of operators. Just call them schematically O1 up to On. How would this be calculated? You'd do an integral over the fields of the theory. You'd have an e to the is, and then you would have O1 up to On. Now, what do you know if you've got a classical symmetry? So a classical symmetry will guarantee you S is invariant. And of course, we're now being more sophisticated. We say up to a surface term, which we neglect anyway. We always neglect the surface terms. So we know this e to the is invariant. What we don't know if the measure d phi is invariant or not. And you really can find situations where the action is invariant, but the measure is not invariant. If the answer is yes, if the measure is invariant, then you have a symmetry. If the answer is no, then there is no symmetry. The symmetry that the classical theory enjoyed is broken by quantum effects. Now, in some of the older literature and older books that you'll read on quantum field theory, they will tell you that this symmetry is anomalous, and they'll talk about that as an anomaly. We're not going to talk about that. If the path integral measure doesn't have that symmetry, then there just is no symmetry, and there's no need to talk about this further. Your theory just doesn't have this symmetry. Nature is quantum mechanical. To really have a symmetry, your path integral measure and your action should be invariant. In the more modern way of talking, an anomaly is actually an obstruction to coupling a quantum field theory consistently to background gauge fields for a symmetry. So you'll have some global symmetry, and when you say you've got an anomaly, you mean you cannot promote that symmetry to be a local gauge symmetry. So a symmetry is anomalous if you cannot make the partition function gauge invariant under that symmetry, under the local version of that symmetry, no matter what local counter terms you add. Good. We'll continue in a moment.